All right, last stuff we're going to get into is factorial ANOVA. So we're going to go through conceptual overview of our factorial designs, talk about main effects and interactions. We're now to the point where you will not be able to escape interaction effects from here through the rest of this school year. We're going to talk about a lot about this stuff. We're going to go through, talk about calculations in factorial ANOVA, effect sizes, confidence intervals, and then go through follow-up test stuff. Okay. So up to this point, we've gone through, talked about one-way ANOVA, looking at the relation of a single categorical variable with some sort of continuous outcome. Again, I've said this before, when you're thinking about how do I go through and approach an analysis, number one thing you need to do is think about, okay, what are my outcomes? What are my inputs? What's the level of measurement? Once you determine those two things, your options for analyses are going to start to sort of get worked down. I mean, it's going to start to limit sort of the types of things the types of analyses that you're going to look at. So again, for a one-way ANOVA, we've got one factor, one categorical variable with two or more levels, right? And we're looking at the relation of that with some continuous outcome, right? In a group-based design, we often talk about this, about group differences across levels of my categorical factor, but I could also talk about this in terms of the relationship of gender to outcome, or the relationship of college major to income, right? Now I might have 4 or 5 different levels to major, right? I might look at business and engineering and liberal arts and communications and econ, right? But I can still talk about that. I can talk about this as differences in these groups on income, or I can just be more efficient and say, what's the relation of major with my income variable, right? So wanting to be flexible about how we're going through and talking about this. Amelia, was this where you were talking about regression and ANOVA stuff? Okay, like this is the same type of thing, right? So we've got, this sometimes will get confusing to people as well. I've got, Kate, I've got 5 different majors that I'm looking at, right? So how many variables do I have here? Okay, that's where that was the trick question you fell for. How many variables do I have? One variable, right? But it's just a categorical variable. There's 5 levels to that, right? So engineering is not a variable because engineering is engineering. That's a constant, right? But wanting to be aware that we can start thinking about these effects in terms of relations with outcomes. We can also think about mean differences across these 5 majors, right? But sort of think about things in terms of relations starts to give us a little bit more flexibility in how we're talking about things, okay? So with our one-way ANOVA, we can also think about our one-way ANOVA as an extension of a t-test, right? ANOVA, or t-test, is just a special case of ANOVA. They're functionally interchangeable. I think what's the relation with F and T? My F and my T statistics, if I just have 2 groups.
Is it F2 squared?
Yep, they're just they're the exact same thing, right? So if I choose to do, I've got 2 tests. I'm doing a pairwise test. I can run that as an ANOVA. I can run it as a t-test. It functionally makes no difference, right? Personally, I'd probably run it as a t-test. That's because that's just convention. That's probably just going to make more sense to people. But functionally, it makes no difference. T-test is just a special case of ANOVA. ANOVA is nice because what we can do is we can start to expand this out. So we're not just looking at restricted to 2 different groups. We've got 3 or more groups going through and looking at our ANOVA models. Okay. The question starts to be, what if we're interested in multiple factors on some outcome? What if it's not just one factor, right? Maybe, Kate, we're not just interested in major. Maybe we're interested in major and gender, right? What are differences in income, eventual income across age or major in gender or degree in gender on income, right? Now we've got not one factor, but we've got 2 factors. We've got one factor that has 5 levels, and then another factor, we'll call it 2 levels, right? How do we go through and how do we account for these types of questions? Because it seems like a reasonable question, right? Well, a couple of things. We could conduct multiple one-way ANOVAs, right? We could look at differences in income, eventual income across majors, and then we could look for differences in income across gender, and then we can sort of make conclusions from there, right? That would be breaking this into a couple one-way ANOVAs. Problem is we now have additional issues with alpha inflation, right? Because we were just running a bunch of tests. We're concerned about that for all the reasons we talked about before. But also we might start to miss specific stuff due to combinations of factors, right? Maybe if we're looking at income down the road, maybe there's something for some types of majors, maybe gender makes a difference. Maybe there's a specific combination, maybe it's not the same across, maybe differences in income across majors aren't the same for both men and women. Maybe there's something else going on there. Maybe the combination of these two things start to become important. This is where we get into our factorial designs, okay? Factorial ANOVA, this is going to be an ANOVA model that's incorporating two or more different factors in the same analyses, okay? Remember our factor, this is just our categorical variable, okay? So we're looking at the relation of two or more variables, categorical variables, on some continuous outcome within our factorial design. This is nice, it's more efficient than multiple one-way ANOVAs, so we're starting to avoid type 1 error, right? So I've got family-wise error associated with this one and a family-wise error associated with that one. Things start to get a little bit tricky there. Also what we find is that our factorial designs start to become more powerful than our one-way designs, okay? And we'll talk about why that is. Basically what we're doing is we're starting to include other things that might account for within group differences, and that starts to reduce our error terms. So one, they're more efficient. Two, we can start to ask more interesting questions. We can also, some benefits here, greater influence regarding generalization, okay? I can go through, if I want to say, so I see that these are differences that we see across different majors, right? Engineers make more money than liberal arts folks, and communication majors make sort of less money than these folks, right? But does that, if we account for gender, if we account for sort of whether or not more men or women are in these majors, does that help account for things? And so we can start including other factors to start seeing whether or not these effects hold as we start to account for more other types of characteristics. And if we do, we can start to sort of make more specific assumptions on the extent to which our effects generalize to the larger population. And then this is the big benefit, is we can start looking at the combined effect of factors on some single dependent variable. This is where we get our interactions, okay? I can go through and say, yeah, I see that engineers make more money than econ folks, but does that hold across men and women, right? Or does it matter that, does that difference, the difference that we see across these different outcomes, is that dependent on gender? Is it the same across all groups, or do we see that men start to make more money than women in certain types of fields, right? This is something that we can't, or that we can't tease apart with a one-way design, but when we start working into factorial designs, we can start to look at these interactions, okay? And this gives us some greater flexibility in the types of questions that we ask, how we go through and start to tease some of these apart, okay? So again, if we're looking at terminology for our factorial designs, factorial design is where we've got every level of factor paired with every other level of subsequent factors. We've got a full factorial design. We've got all combinations of independent variables and all combinations of dependent variables, okay? So if I have three factors with two levels to each factor, how many cells do I have? 6, right? So if I've got, I'm looking at condition 1, condition 2, and gender, right? I'll have, this is A and B, this is X and Y, that's male and female, right? So in our fully factorial design, our 2 by 2 by 2, we're going to have condition A with level A, X male, A, X female. We're going to have B, X male, B, X female, Y, A male, Y, A, Y female, right? So we're going to, actually, no, we've got more than 6. Is that more than 6? So we got, no, that's 6, okay, great. So we've got 6 different cells. All possible combinations of factors are combined with all possible combinations of others. Angela, I forgot markers. Will you go grab some out of my office? Thank you. Thanks. So this can start to get kind of complicated though, right? And so we want to have terminology that efficiently communicates the nature of our design to other people. And so we use our full factorial designs, identified these by the number of and levels of our factors. So a 2 by 3 factorial ANOVA, how many factors do I have? What do you think, William? 2 factors, right? How many levels do I have in my first factor? My first factor.
Oh,
2, right? So I've got 2 factors, 2 levels to my first factor. Emilio, how many levels is the second factor? 3, okay? So I've got, in this design, I've got 6 different cells, right? So we've got 2 factors, A and B, factor A with 2 levels, factor B with 3 levels, okay? Questions about how, I mean, it's a pretty simple system, but it's important in order to communicate. Anytime you're talking about presenting an ANOVA model in any type of thing, you should probably identify just right from the start, this is, I'm looking at a 2 by 3 factorial, or a 2 by 2 factorial, or a 2 by 2 by 3 factorial, or a 2 by 2 by 4 factorial, right? That's telling people, that's an efficient way of communicating how many factors and how many levels to each factor. That helps me get an idea of what your design is looking at, okay? So our cell, this is our subsample involved in a specific combination of factors. So here we have 6 cells in a 2 by 2. How many cells do we have? In a 2 by 2? 4, right? So these are just our individual cells. This starts to become important when we start thinking about screening, okay? Because, this is a spoiler alert, how many groups do we have to separate a 2 by 2, if we want to screen for a 2 by 2 factorial design, how many groups do we have to, individual groups do we have to screen? 4, yeah, right? Because each one of those cells, that's a different population, right? I've got male engineers, I've got female engineers, I've got male econ folks and women econ folks. Those are all separate populations, or samples from all separate populations, and those populations might have different characteristics on income in terms of skew, kurtosis, things along those lines, variability, and so we want to make sure that when we're screening, we're breaking this down appropriately. Our main effect, this is going to be our difference in means across levels of a given factor, collapsing across all other factors, okay? This starts to get a little bit heady. We're going to go through some examples, but if I'm talking about a main effect, like again, my 2 by 2, we're saying, again, let's keep it simple. We're looking at men and women in engineering and econ, okay? Layla, what's my main effect of gender going to be looking at?
that one gender in both majors.
Mm-hmm.
So like men make more money in both econ and engineering when compared to females.
Exactly, right? We're saying collapsing across, if we're ignoring major, we're just looking at whether men make more than women, okay? Haley, what's my main effect of major?
Can you repeat the question?
Yeah, what's my main effect of major? If I've got a 2 by 2 design, I'm looking at, so I've got my one factor is gender, my other factor is major, looking at income. So what's my main effect of degree or major?
These 2 specific majors make more money regardless of gender?
Looking at the differences in income across these 2 majors, regardless of gender, right? So these are both going to be main effects. Looking at the effect of this factor collapsing across all levels of this factor, right? This is going to be different than our conditional effect, or sometimes we call these simple effects. This is going to be the effect of one factor on the outcome at a different, at one level of a different factor. Okay.
Is that the cell effect then?
What's that?
The effect within the cells?
Yeah, and basically that's what we're looking at here is cell differences. So if I do find an interaction of gender on degree, when we're talking about income, that's going to suggest that differences across engineers and economists is dependent on whether or not we're talking about men or women, right? And so our conditional effect here, we're going to be looking at, okay, do men and women, let's say, do male engineers make more money than female, or do male engineers make more money than male economists, right? So we're looking at one level of a factor, or so we're looking at differences in one factor at a specific level of our other factor, right? So we could say, do engineers make more than economists if we're talking about men? And do engineers make more money than economists if we're talking about females, right? We could also swap it around, right? We could really say, do men make more money than women in engineering? Do men make more money than women in econ, right? These can be hard until you get some practice to sort of put together in your head. And so the number one thing you should always do the first thing you should do anytime you find an interaction effect, graph it out. Look at it visually. This is going to help you start to envision what this interaction looks like and how we might start to tease things apart. Okay? But these simple effects, these are what we're looking at, and this is what we have to get into if we start to find significant interactions. And we call these conditioned effect because we say the effect of degree on income is conditioned or dependent on gender, right? Do men make more, do engineers make more money than economists? I don't know. Are we talking about men or women? Because it depends, right? Maybe for men, or maybe women, maybe for men, yeah, engineers make more money than economists. But if we're talking about women, maybe not. Maybe female engineers and women economists make the same amount of money, right? But we do see a difference in men, right? We see that I can't tell you what the difference, whether or not economists make more or less money than engineers, unless I know if we're talking about men or women, right? So this is a conditional effect. We're going to spend a lot of time talking about conditional effects, okay? So here's an example. So we're going to go through, and I've given you sort of handout here, so we're going to make sure you have that. We're going to go through and take a look at that eventually. But to expand our example from our one-way ANOVA, that's a different one, so but never mind, have that on hand when we get to actually run the calculations. So remember, with our one-way ANOVA, we're talking about, we were looking at whether or not temperature has an impact on performance, right? Do people in cool, normal temperature rooms or hot rooms, does that impact performance, right? That's our one-way ANOVA. We have one factor. What's our factor? What's our categorical variable? What do you think, Amanda? Temperature, right? How many levels to that example? 3, okay? So we're saying, do we see differences across these? But where are my people from maybe southern climates? Anybody from southern? Angela.
You count Kansas as southern?
Yeah, kind of, okay. Is Kansas humid?
100% all the time, yeah.
Kansas gets really humid, right? So you might suspect that if we're talking about the impact of temperature on human functioning, well, maybe we ought to start thinking about humidity, right? Because all of a sudden, things start to feel very different if I'm talking about different levels of humidity. So maybe this is what we want. We say, okay, we're seeing an effect of temperature on performance, maybe, but we also want to take into account humidity. Do we see differences in terms of high and low humidity? So in this, what kind of factorial design are we working with here, Kate?
2 by 3.
This is a 2 by 3. 2 by 3 factorial design. We've got 2 levels to our first factor, humidity, low and high. We've got 3 levels to our temperature factor. 70 temperature, low humidity, 80 degree temperature, 90 degree temperature, low humidity, 70, 80, 90 at high. We've fully crossed these. This is a fully factorial design. Okay. People see sort of how this is all fitting together? All right, cool. So, 3 different questions we're going to ask with this design. 1, what's the effect of factor A on outcome? Okay? What's the effect of humidity on performance, right? If we collapse across temperature, right, do we see differences in performance at high and low humidity? We also have an effect of factor B. What's the effect of factor B on outcome? What's the effect of temperature on performance, right? If we ignore humidity, do we see differences in people who are working 70, 80, 90 degree temperatures? Okay. And then finally, what are the combined effects of factor A and B on outcome, right? What's the impact of specific combinations of humidity and temperature on performance? This is where we're looking at these individual cells. Do we see a different pattern of means based on the combination of temperature and humidity? So if we're thinking about our main effects, and this will be important when you're going through and looking at sort of noting your individual hypotheses. Main effect of humidity, okay? We've got our null hypothesis is that mean performance at low and high humidity is equal. Here we only have 2 factors, or 2 levels to the factor, so we can just say low and high are not equal to one another. Makes some sense. John, where am I seeing the main effects of humidity?
It would be the 80 and 70.
What's that?
The like 80 and 70.
Right here? Yeah, exactly, right? This is where we're seeing our main effect of humidity. So mean across, so collapsing across temperature, right? Average performance of people in low humidity is a score of 80. Collapsing across temperature, mean of people people in high humid conditions is 70. Okay, this is our main effect of humidity here. And what we're going to do in our ANOVA model is we're going to look at this in our F test. We're going to get an F test specifically for our main effect of factor A. This is going to be the observed variability across. Oops, this should be humidity means. Sorry, Angela, can you email me and tell me to correct that? This should be humidity, not temperature.
Yeah.
Okay. So observed variability across humidity means over the expected variability, assuming that the null hypothesis is true. Okay. So again, thinking about this in our test in terms of ratios, what's the difference that we saw, and is that substantially larger than differences we would expect due to just sort of random chance? Okay. We're also going to see a main effect of temperature. Here we've got 3 levels to our temperature factor, and so our null is going to be 70 equals 80 equals 90, everything's identical, but we don't have one alternate hypothesis here, right? So we can't just put this in mathematical notation. We're going to write out a sentence, we're going to say mean performance differs in at least one temperature condition, right? At least one of these is different than one of the other ones, okay? And Evelyn, where are we seeing our main effect of humidity? On the bottom. Okay, so collapsing across, temperature. Collapsing across humidity, we're seeing average performance at 70 degrees is 80, a score of 80. Average performance at a temperature of 80 is 75. Average performance score at temperatures of 90 is 70, collapsing across humidity. Okay, people seeing how we're getting and interpreting these main effects of humidity and temperature here. Anybody confused? Because this is a confusing thing. Okay. All right. Here, yeah, you got this switched around, I guess. Again, what we're doing is we're looking here at observed variability across our mean levels here over the expected variability, assuming that these are all drawn from populations with the same mean. Okay. So these are our main effects. But now when we get into our interaction effects, interaction effects are telling us that across our individual cells, across our individual conditions, we're seeing differences that exceed those expected based on our overall main effects. There's more going on across these cell differences then we would expect or can be captured within our main effective factor A and main effective factor B. From a conceptual standpoint, and again, anytime someone says, hey, there's an interaction of A and B, what does that mean? By definition, it means the effect of factor A on the outcome is dependent on factor B. You don't have to know anything else about what people are studying. If there's an interaction, you say the effect of X on Y is dependent on M, right? Or the effect of M is on outcome is dependent on Y, right? Or differences in across groups in this factor depends on which level of the other factor that we're talking about. So these are dependent. These are where we start to see those conditional effects, right? If you ask me what's the effect of factor A on my outcome, what's my answer? I don't know. What's the level of factor B? Because I can't tell you unless I know what the level of factor B is, right? And so for this example that we're talking about, or that we've been working with, interactive effect would suggest that the impact of humidity on performance depends on the temperature, right? So you say, what's the impact of humidity on performance? Like, I don't know. How hot are we talking about? What's the temperature? If I know that, then I can tell you, but otherwise, the effect of humidity on performance changes depending on what type of temperature that we're talking about. Conversely, we can say the impact of temperature on performance depends on what level of humidity we're talking about. We're going back and forth here. We need to know both of these things in order for us to make a specific conclusion. Okay? So our interaction effect of humidity by temperature, our null hypothesis, the effect of humidity on performance is independent of temperature, right? Or you could say doesn't depend on temperature, or sort of however you want to state that. And your alternate hypotheses, again, you not have a specific hypothesis here. You're just saying that the effect of humidity depends on temperature. So, if we're looking at our table of means here, okay, so we're seeing main effect here and main effect here. John, are we seeing an interaction effect in these means? What do you think?
I guess how would you be able to tell?
Okay. Tricky. Anybody have a thought? Anybody? Do we have an interaction here? Or do we not have an interaction? And how would we tell?
I think we would.
You-
Because if you look at both, if you look at all the cells on the top are roughly 10 or are 10 higher than the ones on the bottom, and you can see the same effect going column by column as well.
Okay. So and you say you think this means we have an interaction effect.
I think one would be different.
Okay. Well, it's a good guess, right? But if I'm looking here, it looks like this is kind of the same thing. Overall, so we've got a main effect of humidity, right? People in low humidity are reporting about 10 points higher than people in high humidity. And we see that the same here, the same here, the same here, right? And we're seeing as we go from 70 to 90, we see a 5-point reduction in each one of these, right? So we're seeing 85, 80, 75, 75, 70, 65. So we kind of got the same thing going on in both of these. So we're seeing here, we're saying main effect of temperature in both conditions. Here, we're saying main effect of humidity in both conditions. So these means aren't the same, but are we seeing an interaction effect? Not really, okay? What about this? We're seeing an interaction effect here. What do you think, Haley?
Yes,
Yeah, how do you know that?
because for low humidity and high humidity at 70 degrees, they're both the same.
Uh-huh.
And then it's also high humidity at 80 and 90 are different.
Mm-hmm. And what about at 80?
It's 10 there and it's 20 at 90.
Right? So here, if we look at performance at 70 degrees, high and low humidity is about the same. Then if we look at 80, all of a sudden we've got a difference. Then a 90, all of a sudden we got a bigger difference, right? So it looks like differences in humidity, differences in performance across high and low humidity start to become dependent on, sort of depends on which temperature condition we're looking at. If we go the other way, what are, Layla, what are scores doing at low humidity?
They're pretty consistent.
They're pretty consistent. So at low humidity, is temperature having an impact on performance? No. What about at high humidity? What's going on here?
We see a reduction.
You see a reduction, right? So at this level of the factor, temperature doesn't seem to have an impact. At this level of the factor, it looks like temperature might have an impact, right? And so this would be consistent with a probable interaction effect, because the pattern of means starts to depend on what level of the factor we're looking at. If we go back and look at this, patterns of means is the same. This one's higher than this one, but it's higher by all the same amount. And things start to decrease as we look at 70, 80, 90, but it's all decreasing by the same amount, right? And so what's going on here, in this situation, differences in our means are captured perfectly by our main effective humidity and our main effective temperature. But here, we see the same main effective humidity and temperature, but our individual pattern and mean starts to change up. Okay. So this is why graphing these start to become really important. If we go through and we graph these data, is it easier to see the interaction? Yeah, Amelia, why, and so people get tripped up with this. How are you seeing an interaction when we plot these graphically?
Once the terms cross.
What's that?
Once the terms cross.
Mm-hmm. Right? So we're seeing here, and your interaction effects, they may not cross within the range of values that you're taking a look at, right? But what we're looking at, if we're looking at just main effects, we're seeing functionally parallel stuff, right? In a line graph, you're seeing parallel lines, right? So we can see a main effective humidity in that people at the low humid thing are scoring higher than the performance in the low humid conditions are all higher than the high humid conditions, right? So we've got a main effect of humidity here, and we also looks like we have a main effect of temperature. As temperature increases, performance decreases, right? But do we have an interaction? No, right? Because those lines are all doing exactly the same thing. If we look over here at our second panel here, though, now all of a sudden we see something different, right? It's very easy to see that we have what looks to be like an interaction effect here, because, and we can still see a main effect of humidity, right? Because if we take this mean, and this mean, the combination of those scores and the combination of these scores, overall, who's performing better? People in low humidity or high humidity? People in low humidity, right? And in general, if we take the average of these scores, and these scores, who's doing better? People in low temperatures or higher temperatures? Lower temperatures, right? But these two patterns start to diverge depending on what specific combination that we're talking about, right? And so this is why it's important. Anytime you get an interaction effect, very first thing you should be doing is going through and graphing that out. Excel is a nice way to go through and graph these out and so start to take a look, so you can start to get an idea for the nature of your interaction effect. How goes through and provides a number of different graphs also that are demonstrating interaction and non-interaction effects. So again, each one of these, the profiles across your two groups are all identical, right? So we have a main effect of factor B here, right? In that B1 is bigger than B2. Do we have a main effect of factor A? Nope. So here we have a main effect of factor B, no effect of factor A, no interaction. Okay. What about here? Main effect of factor B? Yeah, probably, depending on our sample sizes and our standard errors and stuff like that. What about a main effect of factor A? Yep, also have a main effect of factor A. Any interactions? No, right? Same thing here. Main effect of factor B, we can see on average our B groups are higher than our B1s are higher than our B2s. Main effect of factor A in that, yeah, it looks like so there are differences across my factor A's, but an interaction, probably not, right? Because these two slopes for each one of these conditions of the pattern of means is identical. But if we look at these, now all of a sudden, we have some interaction effects. Here at B2, is there an effect of A at B2? What do you think, Nick?
Effectively, no.
No, right, because they're all the same, they're all identical. What at B1? Is there an effective factor A on at B1? Yeah, all of a sudden factor A starts to make a difference because as we step up, we step up. Same thing here, right? This is a kind of a classic cross pattern here. At levels of factor B, at level 1 of factor B, as A increases, our outcome decreases. At second level of factor B, as A increases, our outcome increases, right? So we've got a different thing going on depending on which level of factor we're talking about. Same thing here, we've got kind of a different sort of parabolic thing going on at factor, across A at factor B. We've sort of got an inverse thing going on. Here we've got a U shape going on. It's much easier to identify potential interactions if you've gone through and plotted out those means, and then you're saying sort of, are these things sort of similar to one another, okay? Interactions are a hard thing to wrap your head around, but people kind of visually kind of get the representation of what we're looking at in terms of main effects and interactions. Okay, cool. We can also represent these things, these interactions in terms of bar graphs, and this is actually my preferred way of presenting between design, or between subjects groups. If we're doing repeated measure stuff, this starts to make more sense because it looks like, oh, these are the same, this is the same group of people I'm following across time points or conditions. But if I'm using between groups design, I think bar graphs are probably an easier way to represent this, right? So again, if we're taking a look at our temperature humidity data, here we go. We have performance at high and low humidity at 70 degrees, 80 degrees, and 90 degrees, right? And even though we've seen differences, right, we're seeing that this difference, the nature of the difference, is identical across each one of these groups, right? So if we look at differences in high and low humidity across these at 70, it's about the same as the differences at 80, is about the same differences as 90, right? It's all identical. And if we look at high humidity, it's all decreasing at the same rate as low humidity. So we're seeing main effects of humidity and main effects of temperature, but no interaction here, okay? One thing you can do, this is a trick, if you're having a hard time trying to remember whether or not you have, interactions are easy to see with lines. Bar graphs provide I think a more intuitive way of presenting mean-based stuff. But if you want to go through and draw a line from the sort of top point of each one of those bars, and if you do that, you're going to get the same two parallel lines as you did previously. Okay, they don't have to be exactly parallel, but if they're roughly about the same, probably suggests you don't have an interaction. However, if we go through and bar graph our second scenario here, we start to see something very different in terms of our patterning of means, depending on whether or not we're talking about high or low humidity, right? At low levels of humidity, is temperature making any difference at all? Nope, right? It's the same, right? But if we start to crank up the humidity, right? We put this 80–90% humidity, as our temperature starts to go up, performance starts to decrease, right? It starts to flag. If we go through and we take and draw a line across here, there's a line across here, you start to see that we do have that cross pattern there. Questions about this? I mean, I don't want to rush through the concept of interactions, because it starts to become, it gets tricky when you get into your day-to-day. Like, okay, we've got a main effect, we've got an interaction. Like, so what does this all mean? I want to make sure at least at this point you have or at least kind of seeing it as we're talking right now. Questions? Yeah, John.
So like for the bottom example, it's basically just the effect of high humidity depends on the temperature. Exactly. That phrase right there should be seared into your brain in terms of talking about any type of interaction, right? It's even helpful when you're starting to talk about higher order, like three-way interactions.
Some people say, oh, you can't interpret a three-way interaction, that's garbage. You can, so you just need to sort of have a strategy. The effect of temperature depends on humidity, or because these are mathematically interchangeable, I can say the effect of humidity depends on temperature. Both of those are correct. How you go about and start to probe these interactions is going to be based on theories or your conceptualization of what's going on, right? But let's say I had a three-way interaction, right? Let's say I had temperature, humidity, and task difficulty or something like that, right? And I found a three-way interaction, right? What I could then say, and so task difficulty is hard and easy, right? I would say if I had a three-way interaction, I could interpret that by saying the interaction of temperature and humidity depends on task difficulty, right? So what I would have is I would have a panel that's looking at the interaction of humidity and temperature at low task difficulty, and the interaction of temperature and humidity at high task difficulty. And then there's a bunch of different ways we can start to tease that apart and show how we're going to go through and do it. But we could, without too much difficulty, go through and start to graph that out to try and get a sense for what's going on with this interaction. Other questions? All right. So here's a question. Should we interpret main effects in the presence of reliable conditional effects? So, in this situation, right, I've got a main effect of humidity, right? People at low humidity in general perform better than high humidity. And we've got an effect of temperature in general collapsing across humidity. People's performance decreases as temperature increases. Should I interpret main effects when I have in the presence of a significant interaction? Yeah, Laura says maybe. I'm kind of with you, maybe, right? Sort of depends. Some people often are taught that you cannot interpret main effects in the presence of, or you never interpret main effects in the presence of interaction. Generally, it's probably a decent rule to follow, because if I say, oh, so if I'm looking at this right here, right, Amanda, and I say, and you say, what's the impact of temperature on, or excuse me, humidity on performance? I'm like, oh, you perform better in low humidity than high humidity, right? Why might you say that that's incomplete? If this is the panel we're looking at.
Well, because it's not true across the boards.
Exactly, right? It kind of depends, right? In general, collapsing across temperature conditions, yeah, in general, people perform better at low humidity than high humidity, but that doesn't tell all the story, right?
At a certain level, they're the same.
At certain levels, they're the same, right? And so people will say, well, so I can't make an interpretation of this main effect because that that effect isn't actually a main effect, it's a conditional effect because it changes depending on what temperature condition we're talking about. But there are certain situations, right, that main effect can start to become important even if there's an interaction effect. Let's say I'm doing health-related research and I'm saying, is smoking bad for you, right? And I'm looking at the impact of cigarette use and age of starting smoking or something like that, right? I may well find an interaction effect there, right? Where the health consequences of smoking is dependent on when you started smoking, right? And let's say if you started smoking at 8, right? The long-term consequences of smoking are sort of more severe than if you started smoking, say you're 50 and you start smoking cigarettes for some reason, right? Right? So then, well, is cigarette use bad on or have an impact on cardiovascular health? I might just say, yeah, it's not good. People on average regardless of when you stopped, smoking is bad. Smoking is not good. Smoking has a negative impact on your health. Now, this is part of a conditional effect where we see that effect starts to become more severe for people who are starting at a younger age, right? But at the end of the day, if the question is smoking bad for your health, I'm not gonna sort of like equivocate or be like, no, it's bad in general. It just looks like it gets worse the younger you start to you take on smoking. Okay, and so this starts to become important in sort of thinking about in general. Yes, if I'm running sort of my general analysis, right, and I see an interaction, probably what I should start doing is say, I found an interaction effect of this factor and that factor, and then we're going to go through and jump into specific conditional effects, right? But in some situations, that main effect might be important, right? You might want to talk about it. You might say, we found a main effect of X suggesting that outcome is worse in this group as opposed to this group. However, this main effect is qualified by an interaction of X and Y, right? And then we're going to go through and start sort of looking into some other stuff, right? So I would encourage you to be flexible, right? In general, probably what you're going to do is focus straight on the interaction effect and then sort of start to work on pulling things apart. But you may run into situations where that main effect is actually an important question, right? And so if anybody tells you you can't interpret main effects in the context of interaction effects, well, yeah, that main effect doesn't tell the whole story, right? There's more to it than that. But in general, big picture stuff, smoking's bad for you, don't do it, right? So wanting to keep that stuff in mind. Okay, so again, trying to keep you off of, oh, these are rules of thumb, this is how we always go about sort of doing X, Y, or Z. Questions about this? All right. Another thing that comes up, right, is it's important to recognize that in a fully factorial design, the main effects and your interaction effects are independent of one another, okay? These are orthogonal effects by design, okay? These are things that are independent of whatever's happening on your other factors. So let's take, in this, again, a 2x2 design here. Here we have a main effect of factor A, right? So we see collapsing across levels of factor B. We see that people who are in condition A1 are scoring systematically higher than A2. Okay? But no effect on B. Collapsing across A, people in B1 and B2 doing the same thing. Okay? People see this? Okay. Here, main effect of factor A and B, right? So here, collapsing across B, A1 is scoring lower than A2. Collapsing across factor A, B1 is scoring lower than B2, right? Do we have an interaction? No, right? One out of nil.
Sure, parallel to each other.
Yeah, right? So we got a 20-point reduction, or 20-point increase, 20-point increase, 10-point difference, 10-point difference. They're doing the same thing. There's no interaction effect here, okay? Here, we have an interaction effect with no main effects, right? If I look at A1 and A2 collapse across B, they're identical. If we look at B1 and B2 collapsing across A, they're identical. But if we look at what's going on in those individual cells, we see an interaction effect, right? We see things that are increasing across B1 and B2 at levels of at A1, but things decreasing at levels across from A1 or B1 to B2 at levels of A2, right? This is another thing too. People say, well, it happens in regression sometimes, right? Like, oh, you can't interpret an interaction effect in the absence of main effects. It's categorically false, because this is what's going on, right? What you could be doing is missing the most important and interesting thing that's going on in the whole thing, right? On average, if we look at differences across A and B, we don't see any differences. And if we look across A1 and A2, we don't see any differences. If we look at the combination of those, we're getting very clear something very different is going on with this stuff, right? And so I'm not sure what textbook someone used at what point we were saying you can't interpret interactions in the absence of main effects, but you missed the boat at some point, because again, these are independent of one another. Whether or not you have an interaction is completely independent of what's going on in main effects of factor A, main effects of factor B. You kind of see this, understand what's going on here? Cool. All right. So, for a two-factor ANOVA, right? So we've got factor 1, factor 2, 3 separate omnibus effects, and each one of these has its own unique, specific set of hypotheses. We've got a main effect of factor A. So we say an independent effect of factor A on outcome. So ignoring factor B, we see differences across levels of factor A. Also have main effect of factor B, and this is going to be our independent effect of factor B on our outcome, controlling for stuff that's going on A, right? So ignoring A, we see differences across levels of factor B. And then we have our interaction of A by B, suggesting that A and B together provide some sort of unique impact that's not captured by main effects of factor A, main effects of factor B. This is our interaction effect. And we're going to start talking about, this is actually a moderation effect. We'll start talking about that next semester. But basically what we're saying is the influence of factor A is dependent on factor B, right? Or we can flip these around because it's interchangeable. The main effect, the effect of factor B is dependent on factor A or conditioned on factor A, right? So if you ask me what the main effect of factor A is, I don't know. I need to know what levels of factor B we're doing, because the effect of A differs depending on what level of factor B we're talking about. Okay. How are we feeling about this? Comfortable? Okay, cool. Let's do this. We're going to jump into calculations, but let's take a quick, we'll do 10-minute break, come back here at 3:30 and jump into this stuff. Okay, folks, now for real, this is where you want to have your sheet with the data sheets that you have as we're working through calculation of factorial ANOVA. Now, your opportunities to calculate factorial ANOVA by hand are probably going to be limited to this class. Like, this is not something that you will do likely. But I think, again, as we start to get into more complex designs and more complex types of analyses, you'll start to have to go through and recognize where different sums of squares are coming from and things along those lines. So going through and doing this by hand is not just to torture you to make you do longhand calculations, but hopefully try and give you a sense for where these values are coming from, that it's not just black box stuff coming out of nowhere. So when we're calculating our factorial ANOVA, for a two-way factorial ANOVA, and this will extend to higher order models as well, what we start out with is our total variability. This is all the variability in your data. Okay? And just like before with our one-way ANOVA, we're going to section this off into our within treatment variability and our between treatment variability. Layla, what do we call our within treatment variability? What do we conceptualize that as? Error, exactly, right? Because if performance on my outcome variable is completely dependent on whatever my predictors are, what should everybody's score be within each one of these cells? It should be not just simply the same, right? But it's not. We're going to get differences across people, even within cells, due to individual differences and due to unmeasured factors. And even if it's systematic stuff that we could model, if we haven't modeled it, what do we call that, Amanda?
Standard.
Not just standard, but error. Yeah, just this is an error term. It's stuff that we haven't explained in our model. That's where this is going to go. But then we're going to have between treatment variability. This is going to be the stuff, systematic variability, that we can attribute to or link to some of our predictors. Now, in our one-way ANOVA, this was the end of the story. We just had between and within. In our factorial ANOVA, we're going to take that between treatment variability and we're going to break it into variability due to factor A, variability due to factor B, and variability due to your interaction term here. Okay, so things get a little bit more complex, but we're following the same general idea as before. Now for our, as we go through and we're doing hand calculations, two-factor ANOVA table, we're still going to have our sum of squares, degrees of freedom, mean squares, and our test statistic, but now we're going to have variability attributable to factor A, variability attributable to factor B, to the interaction, our error, and our total here. Okay, so we're just kind of splitting the pie up a little bit differently than we had before. Okay, so we're going to start again with our sum of squares total, just because this is a nice place to start at the top of the hierarchy here. Sum of squares total, thinking about this conceptually, is the total variability in your entire set of scores. So conceptually, how we're going through and we're calculating this, this is going to be the sum of your squared deviation scores of person I in group on level J of factor A and level K of factor B minus your grand mean squared. So this is the deviation of everybody in the entire study's score from the grand mean of everybody in the thing, right? So this is the grand mean. Your variability is all the differences, or this is capturing, and it's a sum of squares. Remember, the sum of squares is just a measure of variability, right? Same thing as variance is just a measure of variability. Standard deviation, a measure of variability, right? Your sum of squares is just a metric that is just the sum of your squared deviations, right? So sum of squares total is the difference of everybody in the entire study's score from the grand mean, okay? This notation, don't get scared by this. We're just saying that this is the sum of the squared deviations of, or I guess, person K at level I of factor A, level J of factor K from the grand mean. Okay. So this is conceptually what's going on. Computationally, with the appropriate summary statistics, we can calculate this shorthand by taking the sum of all your squared x values minus the square of the grand mean over the total number of people in the sample. Okay. So again, think about this as all the variability in the sample. This is the whole piece of the pie. And what we're going to do is we're going to split this into between, within treatment variability, separate these out. Okay. Your degrees of freedom for your sum of scores total is going to be one less than the total number of scores in the sample. So big N minus 1 here. Okay. So this is actually the same idea as with our one-way models. So with our two-factor calculations here, if we're using our computational formula, right? Sum of scores total is the sum of our individual x scores minus g squared over n, or excuse me, the sum of our squared x's. If you take a look at your handout here, the sum of your squared x's, so if you took every value, every score in the entire study and squared it and added it up, it's going to give you 840. Did you not get one of these?
Is that what you can say?
Yeah.
That's the arousal one that I have. Are we doing the arousal one or the temperature?
Yeah. So with oh, I'm sorry, I should have sort of said. So what we've got here, we have a 2x3 design that we're working with. So we've moved off of temperature. Temperature was last time. Moving on to this one. What we're looking at here is the relation between task difficulty and arousal on performance, right? So the idea is that in terms of arousal, the impact of arousal on performance, right? Amelia, you're shaking your head. What, from a theoretical standpoint, what's the relation between arousal and performance?
Usually as things get harder, our performance goes down.
Right. So as we get activated, our performance tends to increase, but maybe to a point, right? If we get over activated, then our performance starts to decrease, right? So you think about this as sort of that inverted U curve, right? Well, our performance peaks at some optimal level of arousal, and if we're too low, if we're sleepy and tired, performance suffers. If we're overly anxious and about to have a panic attack, our performance suffers. There's probably a nice level of activation somewhere in there, right? But maybe that level of activation depends on whether or not we're talking about difficult or hard tasks, right? Maybe there's something different going on, right? And so what this example is looking at is the impact of task difficulty with two levels, easy versus hard, and arousal level, low, medium, and high, on some sort of performance, okay? So we're looking at main effect of task difficulty, main effect of arousal or activation, and then the interaction of those two, okay? So again, if we go through and take a look at your handout, if you were to go through, and I sort of summed this up for you, if you take each one, everybody's score and squared it, and then added it all up, That's what you're gonna get here. So we take 840 minus 120, that's the grand total. Yep. The grand total, square that over total number of people in the study is 30. Degrees of freedom, 30 minus 1, and that's going to give you sum of squares total is 360. Degrees of freedom is 29. Okay, so think about 360. 360 is the total units. That's the total. That's all the pieces and components. That's all the parts that we have to work with. All of our sums of squares will sum up to 360 because that's the total that we're working with. Okay. Questions about this? All right. Now what we're going to do, we're going to jump into sum of squares error. Again, this is going to be conceptually the exact same thing as we had talked about before with our one-way models. Our sum of squares error, this is a variability within each condition or group. Okay, so within each cell, what's the variability that we're looking at, right? And so our sum of squares error here, we can conceptually think about this as the sum of the square deviations of person K at level I of group A and level J of group B minus the mean of their cell, right? So again, sum of the square deviations of person K at level I of factor A and level J of factor B from their respective cell mean, okay? So again, if we're thinking about this and how we go about screening these types of analyses, right? We're wanting to see to what extent are people deviating from their cell mean, okay? And then we're going to do that for everybody within the study. We can also do this computationally by just adding up the sum of squares per group, or we could get this by subtraction. We could take sum of squares total minus sum of squares cells. We're going to calculate sum of squares cells later. We don't have that yet. But again, sort of wanting to see that all this stuff fits in with one another. So again, our sum of squares errors are variability within cells that's due to individual differences, experimental error, just random stuff that's going on. Okay. Degrees of freedom for our sum of squares error is going to be given as the product of our levels of factor A, levels of factor B, and the number of participants in cell minus 1. So our degrees of freedom error, we can calculate this as the number of levels of factor A times the number of levels of factor B, and take all that by the number of people per cell minus 1. We could also calculate this by subtraction. If we take degrees of freedom total minus degrees of freedom A minus degrees of freedom B minus degrees of freedom of the interaction, get the same thing. So if we're using our sheet here and we're looking at calculating sum of squares as the sum of our sum of squares per group, what we can do, if you look at your handout there, we see sum of squares for people in the low arousal easy group, plus the sum of squares for people in the medium arousal easy, high arousal easy, low arousal hard, medium arousal hard, high arousal hard. If we add up those sums of squares, we're going to get our sum of squares error. Degrees of freedom calculated as we've got 2 levels to factor A, 3 levels to factor B, and we have 6 people in each cell. 6 minus 1, that's going to give us, within treatments, our sum of squares error is going to be 120, 24 degrees of freedom here. People see how we calculated that?
Where did the 5 come
Oh, if you see, we got 5 people in each cell. We've got a balanced design, 5 people per cell. So small n is going to be the cell size, big N is going to be all the people in your study. Other questions on this? So again, here, total piece of the pie. Everything we have to work with. Here, we've got our total of this. What portion of this is attributable just random stuff going on within each cell that we're not accounting for? Conceptually, people see how this is looking? All right. Then what we're going to do is we're going to look at variability attributable to factor A. Okay. This is going to be variability, or in this case, if we've only got 2 levels, the difference across levels of factor A. Our computational formula is, so this can kind of be a little bit difficult to sort of get if you're not familiar with the notation. But essentially what we're doing is we've got the sum of squared deviations for the mean level of I of factor A from the grand mean multiplied by the cell size and the number of levels of factor B. Okay? So basically, we're looking at our sheet here, right? What we're doing is we're going to go through and we're going to take the mean of each, the mean of factor, if factor A is difficulty, okay? If we take the mean of the easy condition, right? What's the mean of my easy condition? 6, right? People see that in the end? 6 minus, what's my grand mean? 4, right? So 6 minus 4 squared plus, what's my mean of my hard? 2. 2 minus 4, square that. So take that sum, multiply it by the number of people per cell is 5, times B is going to be the level of, number of levels of my factor B. How many levels do I have there? 3, right? That's going to give me my, by definition, my sum of squares A, right? And again, this is just saying sort of how much variability is there across levels of factor A collapsing across factor B, okay? We can get this in a shortcut. We take the sum of our row total square, the square of our row total over the total number of people in our row minus our grand total squared over the total people in the sample. And then our degrees of freedom are just going to be the number of levels of the factor minus 1. So if we calculate sum of squares A is the square of our row total over the sample size in our row minus the grand total over the total number of people in our sample, we're going to get row total for easy is 90, so we're going to square that. And how many people in each in all of our easy condition? 15, right? Plus row total for our hard condition is 30, square that over, again, 15 people there, minus our grand total, 120, over total number of people in the study, 30. That's a shortcut to give us our sum of squares across levels of 4 levels of factor A collapsing across factor B. Degrees of freedom, number of levels of factor A minus 1, 2 levels of factor A minus 1 is going to give us 4 factor A, sum of squares of 120, 1 degree of freedom. All right, people see kind of how we've sectioned this off and why this is important. Okay. Same thing with factor B. Factor B is going to be the same thing. This is just going to be the variability or difference across levels of factor B. Nick, remind me why we're talking about variability here instead of just looking at differences across our means.
Can you repeat?
Yeah, so I'm talking about variability across levels of factor B. Why don't I just say, why don't I just look at the differences across levels of factor B?
So you want to look at the variability in relation to your overall variability.
Yeah. And so why did I bring variability into the equation here? Why can't I just look at differences like we have been with our t-tests and stuff? Oh, bless you. Anybody help him out?
Could the variability potentially be different?
Okay, I think you're getting there, Haley.
The mean scores might be different, but if they're the same in each condition, not changing.
Right, and so that's starting to get at some interaction stuff. Remember that when we're working with more than 2 levels of our factor, there's not just one value that we can get that sort of captures differences, right? If we're working with pairwise tests, I can say, is level 1 different than level 2? That's the end of the story. I don't have to worry about it, right? But as soon as I get 3, 4, 5 levels in my factor, there's all sorts of different ways I could have a pairwise difference in there, right? So variability, remember, is my way of going through. Variability is my proxy for differences, right? Because if all my means, right? So let's say I have 4 levels to factor A, okay? If I have 4 levels to factor A, but the mean across all 4 of those levels is equal, what's my variance going to be, Amanda? It's going to be 0, right? What if my variance is 1 billion? What does that tell me? Well, if I know kind of what my scaling is, that might tell me a little bit. But it suggests that there are differences, right? Like so I've got a lot of differences across my levels of my factor, right? So variability is just within the context of ANOVA is the way we look at differences. If we have something that's means that are highly variable across levels of the factor, we've got a lot of differences. If there's not a lot of variability, it suggests that there's not much differences, right? And so this is why, you know, I sort of put in parentheses here differences, so just wanting you to think about variability as differences across your means here. Okay. So here, just like we did before, we're going to take the calculate our sum of squares B as the sum of squared deviations of mean of level J of factor B from the grand mean, and then we're going to multiply the sum of those squared deviation scores by the number of people in the cells and the number of levels of factor A here. So we would go through and take a shortcut, calculate this as the square of our column totals over the number of people in each column minus our square of my grand total over n. Degrees of freedom are the same as we did before. They're just the number level of factor B minus 1. Okay. So again, here, if we want to take the shortcut, calculate this as our column total, square of our column totals over our column size over grand total over n. We can go through column total. Oh, yeah, that shouldn't be 90 across all of those. I was supposed to change that, and I didn't in the handout. So if you look, you see your column totals are 90, 90, 90 across the bottom there, right? That's an error. What's up?
I have 20, 50, 50.
Do you have 20, 50, 50? Oh, okay. Well, I've got the wrong one then, so. Okay. All right. So yours are right. Okay. So 20, 50, 50, 120 divided by, or 120 over 30. Okay. Degrees of freedom, you got 3 levels, factor 1, minus 1 there. Okay. So we've got 60 and 2. Okay. So again, if you're thinking about this main effect of factor A, this is the differences we're seeing across levels of factor A, ignoring factor B. This is the differences we're seeing in factor B, across levels of factor B, ignoring factor A. Here is our total within error, and here's the total piece of the pie we're working for. Okay. Anybody guess how we're going to go through and get this?
Multiply A and B.
What's that?
Multiply A and
Okay, not multiply A and B. If this is the total, and so what can we do?
Subtract.
Yeah, we get that through subtraction. Okay. A couple of different ways we can go through and do this. I want you to be aware of sort of calculations. If you computationally, what SPSS is doing in sort of many approaches here, you're going to be calculating something we call sum of squares cells. Okay, sum of squares cells is going to refer to the differences across all cell means. Okay, so variability across all the individual cells. So we've looked at differences across our factors, factor A, factor B. Sum of squares cells is going to be the variability that's across all of our individual cell means. Typically not included in our standard ANOVA tables, but SPSS will give you this in the output. You're going to see a row called corrected model. This is what it's giving you here is sum of squares cells. It's just the variability across all cell means. This starts to become important for the calculation of certain statistics, so I just want to touch base on it here. Primarily what this is going to do is it's going to serve as a computational function, but essentially, if we're thinking about how this relates to ANOVA, sum of squares cells in a factorial model is basically our sum of squares between, okay? Remember we mapped our ANOVA model out as, so this is total between, within, and then we've got A, B, C, or it's not C, A times B, right? This is your sum of squares cells. Sum of squares cells is capturing all the systematic variability within the context of your factorial design, okay? And so sum of squares cells is going to be calculated conceptually as the sum of the square of the mean of factor group I, sum of the square deviations of mean level of I of factor A and the level at J of factor B minus the grand mean, right? Multiplied by your cell size. We can also get your sum of squares cells as sum of squares total minus sum of squares error, right? So we have this total sum of squares, we subtract this error left over, or so we have our total variability, and we subtract variability due to error. All that's left is the systematic variability that is going to get divvied up into different areas, okay? So again, sum of squares cells here is going to be, if we take sum of squares total minus sum of squares within, this is going to be 360 minus 120. It's going to give us sort of our value that's going to be essentially sort of the sum of these three. Okay. So with our two-factor ANOVA, our sum of squares for our interactions always going to be derived from subtraction. There's a couple different things we could go through and subtract to do this, but again, if we're thinking total variability, we've got our between, we've got our within. If we calculate variability due to factor A and factor B, and this is our sum of squares cells, we can subtract these two from this to get whatever's left over, and that's going to be variability due to my interaction terms. So here we can take sum of squares cells minus A minus sum of squares B, and we're going to get our sum of squares for our interaction. Degrees of freedom for our sum of squares interaction is going to be degrees of freedom A times degrees of freedom B here. So here, if we take sum of squares cells minus sum of squares A minus sum of squares B, 240, which is what we would have calculated for it. So if we take 360 minus 120, we get 240 minus 120 minus 60 degrees of freedom for our interaction. 1 times 2 is going to give us 60 and 2, right? Now really, for this, did we need to calculate sum of squares cells? No, we didn't need to. We just take 360 minus 120 minus 60 minus 120. Gonna get us the same thing anyway. Just wanted to, there's that corrected total in your SPSS output. Wanted you to understand where that's coming from, and then again, as you start to move forward and start to calculate different types of statistics, it's important to just kind of know where that's coming from. All right, questions on what we've done conceptually up to this point in terms of calculating or filling in this ANOVA table? All right, so our mean squared and our F test is pretty straightforward, right? Once we've got this stuff, the rest is easy. Sum of squares divided by degrees of freedom is going to give us our mean squared. What's mean squared code for? Well, a certain type. What's mean squared code for in ANOVA? What do these mean squared values represent? Yeah, variance. These are variance estimates. The same variance estimate that we always think about in terms of sort of regular old variance that we've worked on since the beginning of the semester. Okay, so 120 sum of squares divided by degrees of freedom is going to give us a variance estimate. In the ANOVA, we call this a mean squared. So we got 120. We take well, I need to. So I need to should have calculated my mean square within first. So this would be 120 minus 24 is what? Or excuse me, 120 divided by 24 is what? What's that? 5, okay. So we have 120 divided by, is that right? Or did that not work out right? Or no, 120 divided by 24, yeah, 5. Okay, yeah, no, that works. All right, so here we've got our sum of squares divided by degrees of freedom gives us our mean squared. Then we take our mean squared for factor A divided by, that should be 5 right there. Our mean squared error, again, give me an F of 24, because remember our F test is our sum of squares for our factor divided by sum of squares error, give me 24. Factor B, if I take 60 divided by 2, using my mean squared for factor B is 30, divide that by 5, is going to give me 6, and then my interaction, 60 divided by 2 is 30, 30 divided by 5 is 6. Here I've got my main effect of factor A, my main effect of factor B, and then the interaction of the two. Okay. Questions about this?
I have a question for the F critical.
Yeah.
I ran into this on the problem set as well. Like if your F critical is, like I think in the problem set, it's like 41.2 or something like that. Or, sorry, that where you're looking for your F critical value, it's like 241.
Oh,
or
oh, your
341.
degrees of freedom.
Right.
Okay, yeah, yeah.
On the chart, there's not anything for
Okay,
41.
yeah, yeah.
So are you rounding up or rounding down, and then how do you report that, because it's not the critical value for 41
Yeah,
anymore?
I know. So, yeah, what you'll want to do, and I should put this in the thing, you've got, there are online calculators that you can just say, okay, so what's the critical value for an F for 2 and 24 degrees of freedom at 0.5, and it'll give you the exact critical value. So, yeah, I mean, shoot me an email. You already shot me an email. I haven't had an opportunity to take a look at it yet, but yeah, as you're looking at your critical values, go through, and the interwebs is a nice resource for going through and getting those, and I'll shoot you a link to calculators that I use, just so you can find those specific critical values. Okay. Other questions on this stuff? Okay. So again, what we've been working with up to this point are our omnibus tests, okay? And so if we go through and, well, here, I'll just do it right now. So 2 and 24 degrees of freedom. I go, oh, Phil Zimbardo, okay. He's following me from intro Psych. That pretty much captures all of social psychology. It's basically Zimbardo, and that's the end of it, right?
Can't forget Milgram.
what?
Can't forget Milgram.
Right, yeah. All right. So Amanda, if I go critical F calculator, I like this SOPR one, or I mean, it really probably doesn't matter, right? So if I say 2 and 24 degrees of freedom at alpha equal 0.05,
Okay.
my critical F is 3.40, okay? So, if my critical value is 3.40 for an F with 2 and 24 degrees of freedom, then which of these effects are statistically reliable? All of them, right? And so what we have here then is a significant main effect of task difficulty. We've got a significant main effect of arousal level, right? And then we have a significant interaction of arousal and task difficulty in these data, okay? And because the influence of arousal and task difficulty are dependent on one another, right? Because I can't tell you, if Haley says, hey, so what's the relation between arousal and performance? I'd say, well, I don't know, it depends on whether or not we're talking about easy or difficult tasks, right? Or if Evelina asked me, so what's the relationship of performance on task, or the relation of task difficulty on performance? I would say, I don't know. I have to know what level of arousal or activation that we're talking about right now. Because these two things are independent of one another, and because I don't know that arousal or task difficulty is something super, we're not talking about small things, we could probably ignore those and just jump right into looking at our interaction effects here, right? So in the presence of this interaction, we actually don't have main effects, okay? Because this main effect of A is now a conditional effect, right? Because the effect of task difficulty on performance depends on arousal level. And this actually isn't technically a main effect anymore, because the effect of arousal is impacted by task difficulty, right? And so what we're gonna do is we're gonna ignore this and jump right into our teasing apart our interaction effect. So as you're going through and you're writing these types of things up, right, you might note that there's a main effect or a conditional effect of this and a conditional effect of that. You don't have to talk about it, you don't have to interpret it, because what we're gonna do is we're gonna jump right into teasing apart this interaction, okay? And so if we wanna think about how to put this into words, how to communicate this, we could say, based on these data, we have evidence of a statistically significant interaction, which suggests that the effect of arousal on performance is conditioned on task difficulty, or is dependent on task difficulty. When you see conditioned, just think dependent. Okay? And so if we go through and we graph these out, it's pretty easy to see how this, sort of what the nature of this interaction effect, right? Haley, when we're working with an easy task, what's the relation of arousal with performance?
Sorry, we're working with an easy task?
Mm-hmm.
What's the relationship with arousal and performance?
Mm-hmm.
I don't know why I'm finding this difficult. You are at a low arousal for an easy task, it's easier to do. No, it's not. You're doing better than the people in the difficult task, but
Okay, no, sure. And we're ignoring difficult tasks right here, right? What's, if we're just looking at people completing an easy task, what's the relation between arousal and performance?
as your arousal gets higher, you do better.
Perfect.
Okay.
If we're talking about easy tasks, as we go from low to moderate to high levels of arousal, our performance is increasing. So if we're doing something easy, as we start to get more activated, our performance increases, right? But Nick, what's happening what's the relation between arousal and performance when we're talking about difficult tasks?
There seems to be an optimal level of medium.
Right. We've got kind of a moderate, sort of at moderate levels of arousal, we're seeing the highest level of performance relative to people performing difficult tasks at low level of arousal, or difficult tasks at high level of arousal, right? So if you ask me what the relation of arousal and performance is, I can't tell you unless I know whether or not we're talking about higher difficult or easier difficult tasks, right? Or if you ask me the impact of task difficulty on performance, I can't tell you unless I know what level of arousal we're talking about, right? And so there's a number of different ways we can go start to tease this apart, but this is what we'll talk about when we start sort of working through some follow-up tests and interactions. Okay? So there's a number of different ways we can go through and do this, right? We can go and compare sort of this to this to this to this to this to this, and this to this to this to this to this to this, right? So we can look at, essentially, functionally, we could break this down and look at, split this into two one-way ANOVAs, right? We could look at the impact of, or differences in arousal on performance at easy tasks, and the impact of arousal performance at difficult tasks, for difficult tasks. Or we could break this down the other way, and we could look at differences in task between easy and difficult performance tasks at low levels of arousal, at medium levels of arousal, at high levels of arousal. Okay? How we go through and we start to do this is going to depend on our research question and our sort of general understanding, our hypotheses about sort of what's going on with some of this stuff. Okay. Questions about this? All right. GLM stuff, ignore this for right now. So, questions about how we go through and tease apart and looking at specific effects within our factorial ANOVA models. Okay. One of the things we want to think about in terms of our factorial models is thinking about power. Our factorial design is often more powerful than our one-way designs. Okay. And the reason for this is as we start to account for other factors, as we start to account for other things in our model that may be predictive of our outcome, what we do is we start to account for more systematic variability in our analysis, right? Think about adding additional factors is adding additional covariates, right? If I'm looking at performance across temperature, right, I'm like, okay, temperature does a nice job of accounting for performance, but what happens, where's all that variability that's due to humidity levels? Where's that going in our one-way model? Where does that get captured in our one-way ANOVA model? In my error term, right? Because it's not accountable, I didn't model for it, right? And so that's all going in my error term. And if my error term gets real big, what happens to the power of my test? It goes down, right? So as I go through and I start to account for other things that may be predictive of my outcome, what happens is my model starts to get better and I start to have a more powerful model, okay? So again, let's say we have a study looking at self-reported emotional arousal, calm to excited, in response to fear, amusement, and anger eliciting stimuli, okay? So just in my one-way model, this is my total variability in terms of how people are responding to this. And in my one-way model, I'm looking at differences across fear, amusement, and anger eliciting stimuli in terms of predicting total variability here. Everything that's not related to my condition, the film that I'm giving to them, goes in right. I'm going to go through and I'm looking at differences in level of arousal across fear, amusement, and anger eliciting films. But I think I might have gender differences in terms of how people are responding to these film stimuli, right? So what I'm going to do is I'm going to go through and I'm going to model in gender. I'm going to include gender as a factor in this model. Well, now what's going on is now my variability due to my effect is not just based on my film condition, it's also crossed with whether or not I'm working with men or women, and then the interaction of condition and interaction, right? And so what happens is all the variability that was accounted for by gender and interaction, Evelina, where was this variability at in my study one model?
Just account for here.
Yeah, it's all jumped in my error, right? But remember that my error is what I'm dividing all my effects by, and so if this error term is smaller because I've included more things that are accounting for more of the systematic variability in my model, my error term gets smaller, and my effects, my test statistics start to get larger, right? So in general, we think about our factorial models as being more powerful because they're accounting for more of the systematic stuff that's helping account for differences that we're seeing across individuals on whatever outcome we're looking at. Does this make sense? All right. So, I'm going to finish up here with some effect size stuff, okay? So with our factorial ANOVA, we can calculate our eta squared. Eta squared is pretty easy. Eta squared is just our sum of squares effect divided by our sum of squares total. Okay? Can someone remind me how do we what's our practical interpretation of eta squared?
It accounts for error in variability from just broken up.
Yeah, exactly, right? So our eta squared, so I have an eta squared of 0.1, right? And what I would say is there's my eta squared suggests that factor A accounts for about 10% of the total variability in my outcome, right? Pretty straightforward, pretty easy, right? So our eta squared indicating the proportion of total variance attributable to an effect for the sample, okay? Why do I say for the sample in red underline that? Anybody remember?
Because it doesn't transfer to the population.
Yeah, we have a problem with this. it's too big. It's a biased test statistic because it's probably going to overestimate the actual effect, right? So again, eta squared is a nice descriptive statistic for what's going on in the sample, but it's probably not a great estimate of the actual population effect, right? So again, it's positively biased. But what happens when we start to look in, sort of go into our factorial designs, we've got another problem with eta squared, is because our eta squared is going to systematically decrease, all other things being held equal, with the number of effects in my design, okay? So what's going to happen, so I've got a one-way ANOVA, I'm going to have sum of squares effect for factor A, right? But in my 2x3 ANOVA, I'm going to have a unique effect, sum of squares for factor A, factor B, and then the interaction of factor A and factor B, okay? And so what happens is as I start to add additional factors in there, anything that's overlapping with factor A, with factor B, that gets pulled out, right? And so what ends up happening is, let's say factor A accounts for this much of the variability, but now I add in factor B, and there's some stuff that's overlapping with factor A and factor B. Well, factor A only gets stuff that's unique to factor A. So what happens to my sum of squares for factor A as I start to roll in other additional factors? It's smaller, right? And if my numerator gets smaller, what happens to my eta squared? It gets smaller too, right? And so what ends up happening when we're calculating eta squared for an effect, let's say I have a factor A in a one-way ANOVA, right? And I'm saying, oh, my eta squared for factor A is this. Factor A accounts for 10% of the variability in my outcome. As I start to lay in other factors, right? Particularly if I'm not running a tight experimental design where all of my assignments are randomized, right? If I'm using pre-existing factors where things start to overlap with one another, so the unique variability, other factors start to chip away at sort of the unique, what was caught as unique in my one-way design, and so my numerator starts to get smaller. And what ends up happening is that I then have an effect that's not necessarily comparable across all studies, right? Because if I have, let's say I'm looking at the effect of, again, degree on income, right? And someone just runs an effective degree on income, right? I'm going to have an effect size, or I'm going to have an eta squared here, right? But let's say, and then I've got another study that's looking at the effective degree program, but it's also included gender and maybe covariate for family income or something like that, and so on and so forth. All of a sudden, all the stuff that was just kind of related to gender, or excuse me, degree program in my one-way ANOVA starts to get chipped away at my sort of more elaborate design. And so all of a sudden, in my factorial ANOVAs, my effect size is smaller than it is over here, okay? And so we start to have a problem with our eta squared design, or excuse me, with our eta squared metric. And so what we have, and we'll likely use for our factorial design, something we're going to call partial eta squared. Okay, well, not we're just going to call, everybody calls it this, but it's partial eta squared. Partial eta squared is going to be your sum of squares effect over your sum of squares effect plus your sum of squares error. Okay. So who wanted? John, you are hiding back there. I was figured to pick on you. So what's going on? What's the difference? So the numerator is the same in my eta and my eta squared. What's the difference going on in the denominator here?
Instead of total, you have effect and error.
In a factorial design, let's say I've got a 2x2 design, okay? If this is total, what's missing out of denominator and my partial eta squared here.
Your between.
Some of my in-betweens, yeah. For a 2x2 or a 2x2 design, what variability is not being included in the denominator here? So if I'm looking at sum of squares of, let's say I'm calculating eta squared for factor A. So I've got sum of squares for factor A over sum of squares for factor A plus sum of squares error. What's not included? What's missing from this denominator?
The B in interaction.
Be an interaction, right? Because what we're doing with eta squared, we're saying, okay, there's variability due to other systematic factors that we've already accounted for. So we're going to pull that out of the mix, right? And so what eta squared is looking at the proportion of residual variance, or the proportion leftover variance after we've taken out stuff that's already been accounted for other factors, right? So what we're doing, so is the denominator of our partial eta squared, is it going to be larger or smaller than eta squared?
Small.
It's going to be smaller, right? And so what's going to go on is we're going to say, okay, well, instead of looking at sort of what proportion of the total variability is our factor accounting for, partial eta squared is going to say, what's the proportion of residual variability that's attributable to this, right? So if we have temperature, let's think back to temperature and humidity, right? And I want to look at the, want to calculate eta squared for the interaction term, right? What I'm going to do is I'm going to say, okay, what proportion of variability is attributable to this interaction after we account for variability attributable to factor A and variability attributable to factor B, right? If we account for just the differences across humidity and differences across temperature of what's left over, how much of that, what proportion of what's left over is being accounted for by the interaction of these two conditions, okay? And so this ends up being a partial correlation. We're going to get into this much more when we get into regression stuff, right? But essentially, what we're doing is, it's harder to interpret in terms of a practical interpretation, right? But what ends up happening is it ends up being a better metric of comparing across different designs, okay? Partial eta squared also central to the calculation of power. Again, harder to make an interpretation than eta squared. Eta squared is easy. It says for these data, factor A accounts for this proportion of the total variability in our outcome. I can think of it. It's kind of like an R squared, right, for that factor. Here it's a little bit different. I'm saying after accounting for variability attributable to factor A and factor B, interaction accounts for this proportion of whatever's left over, okay? So it doesn't have a nice, sort of necessarily intuitive piece to it, but what it is it's able to go through, if I'm wanting to look at the effect of degree program on income, it ends up being a more comparable estimate than eta squared across different designs. Okay. Another thing, so for classic effect size for ANOVA designs is going to be F. Okay, F has a direct relation to partial eta squared, so we can go back and forth here. Here's interpretive standards for eta and for F here. Okay. But issue with all of these is just like eta squared, or partial eta squared, just like eta squared, partial eta squared, still a positively biased estimate of the population effect. Okay. So what we have is we transition into omega squareds. Okay. Omega, again, preferable, less biased estimate of the population effect. It's still positively biased, but not to the extent that eta squared, partial eta squared is. A nice thing about omega squared, if you want to get into nuts and bolts of things, we can start to tease apart fixed random effects and mixed model types of stuff. I mean, I know that Ben works a lot with trying to calculate effect sizes for some of these, and so it starts to make a difference computationally. If we're talking about random effects versus fixed effects and things along those lines, omega squared, there are different formulas that you can go through and start to account for whether or not we're talking about random effects or fixed effect stuff, which is nice. Now, our omega squared statistics are assuming a balanced or nearly balanced design. So if you have wildly unbalanced designs, it starts to become hard to calculate this. But if you're doing good experimental work, you've got reasonably balanced designs, your omega squared is going to be your best bet. Okay. So depending on the study design, there are different formula that you can go through and use, and different people have proposed different formula. I gave you a handout on effect sizes for ANOVA designs. Go through, read that. Basically, this is just, functionally, it's my notes to myself, trying to combine a number of different literatures and kind of figure out what's going on between different formula, because it's always frustrating if I look at this paper and they have this formula for omega squared, and then I look at this paper and they've got a different formula. Then I have to go through and run through like simulations and make sure that sort of are these things, are we arriving at the same, are these equations functionally equivalent, mathematically equivalent, or am I getting different stuff based on which, based on what formula I'm using, and then that is a headache. But to save you the time and effort, I've gone through and put together several pages of notes that I've passed on to you, so you can go through and take a look at. So go through, take a look at, make sure that you, and this will help you get comfortable in terms of interpreting these statistics, what some of the different stuff is. For the purposes of our class, just use these two, okay? Howell's got some different ways depending on the type of design you're looking at, whether you're talking about how many, what the size of the design, and whether or not you're talking about fixed or random factors. There's different ways of going through calculating omega squared and partial omega squared. For you guys, just focus on this, okay? If you want to calculate omega squared, you're going to take the degrees of freedom. Let's say we're calculating omega squared for factor A. We're going to take degrees of freedom for factor A times our F statistic for factor A minus 1 times the degrees of freedom for factor A times F statistic for factor A minus 1 plus B minus F for B minus 1 plus, if we got 3-factor, 4-factor, 5-factor, don't get in 5-factor models, that's crazy. But we go through plus the total number of samples. So omega squared can get kind of long depending if you're working with really big samples. Partial omega squared, a little bit easier. Degrees of freedom of effect, so let's again say we're looking at effective factor A. Degrees of freedom for factor A times F for factor A minus 1 over degrees of freedom effect, or degrees of freedom for factor A times F for factor A minus 1 plus N. This will give you your omega squared. You'll see variations depending on what formula you're using. Sometimes partial omega is pretty consistent across formula. You get some variation depending on which version of omega squared you're looking at in factorial designs. Talk a little bit more about that in a handout, but for purposes of us, this is what we're going to be working with, okay? And interpretive standards for omega squared, small, medium, and large stuff, okay? We're going to go through an example of this so you can go through, see how to go through and calculate this in practical settings. Okay. All right. Confidence interval for omega squared. Again, this is going to be the same thing we've been doing before. You just take your F, plug your F value in here. You get degrees of freedom for your numerator, denominator. 90% confidence intervals for omega squared, eta squared stuff. Is you get your upper and lower non-centrality parameters, translate those into upper and lower limits. I think I stopped asking you guys to calculate confidence intervals around omega squared. This is how you would do it. We're just not often interested in our omnibus effects all that much, and so it ends up being a little bit gratuitous, but if you wanted to do it, this is how you would go through and approach that. Okay. So, summary of our omnibus effect sizes. Okay. What these are doing, so these eta squared, omega squared, indicating proportion of variability, total variability attributable to a factor. Eta squared being proportion of variability in these data, omega squared being your estimation of population effect. For eta squared, your effective all component plus your error is going to sum to 1. In factorial designs, you're going to assume that your eta squared's conservative in that it's always going to be smaller than your partial eta squared, right? As John noted, your denominator for partial eta squared is always going to be smaller. It's going to give you a bigger effect size. For eta squared, omega squared, you're looking at the total piece of the pie, so it's going to be a smaller, a little bit easier to interpret. Partial eta squared, partial omega squared, this is going to be proportion of residual variability left over after we sort of take out systematic variability that's due to other factors, right? So our partial eta squared, partial omega squared, this is telling us of what's left over after we account for factor A, factor B, what proportion of stuff that's left over is attributable to our interaction term, right? Our individual effects aren't going to sum to 1 because we have some differences in calculating our ratios here. Useful for comparing effects across different study designs. A strength of these types of effect sizes, and particularly eta squared, or these partial coefficients, partial eta squared, going to be important for when we're going through doing power calculations and things like that. G power, want to calculate power of an individual effect within the context of a specific design. Going to go through, we're going to select our F test. We're going to ask for a statistical test. You're going to look for fixed effects, special main effects and interactions, right? We're going to ask for a priori power, input parameters. G power is going to ask for an F statistic. If you go through and you hit determine, we can go down through, you can just say direct and just plug in your partial eta squared, drop partial eta squared in there. Alpha level, power, degrees of freedom in your numerator for your effect. So main effect is going to be levels of factor A minus 1. So if we're looking at a main effect of factor A in terms of your ANOVA test, how many levels of factor A do we have? I think, Laura? 3, right? If we're in interaction, it's going to be the numerator degrees of freedom is A minus 1 times B minus 1, right? Number of groups is just the number of cells, okay? So if we have say we have 2 factors in this design. So what design are we looking at right here? Yeah, a 2x3 or 3x2, right? So just making sure that you're going through, entering all this correctly, and then you go through calculating. It's going to give you total sample size 24. We got a pretty massive effect size here, so basically I need 4 people per cell. I'm excited about that if that's my thesis, right? Okay, so that's just showing you how to plug stuff into G-Power. Questions on this? Okay, where are we at? Okay, we got 30 minutes left. Let's jump into screening for our Factorial ANOVA. So, if we open up so the 2x2 ANOVA expressive behavior, okay? And then grab the screening form here. So what we've got with these data is we're interested in looking at maybe expressive behavior, right? And we want to take a look at the impact of are people equally good at it inhibiting negative emotion and positive emotion? Okay, so we've got a 2x2 design here. Our first factor is film. So what we're going to do is we're going to bring people in, we're going to set them down, we're going to show them either a film that's intended to make them kind of sad, or we're gonna show them a film that's supposed to be funny and amusing, right? So our first factor, our film factor, we've got two levels to this. Sadness, humor, in terms of which film people have randomized to. And then we're gonna randomize people to an instruction condition, okay? In one group, or one condition, we're gonna tell people, just go ahead and watch the film sort of naturally, right? Other condition, we're gonna say, what we want you to do is to inhibit all the expression of all emotions so that if someone were watching you, wouldn't be able to tell what you were feeling at all, okay? And so we've got a 2x2 design here, and so in our individual cells, we're gonna have people who watch a sad film and are allowed to express, people who watch a sad film who are allowed to, or told to inhibit their expression, people watch a humorous film, allowed to express, people who watch a humorous film, told to inhibit their emotion. And what we're doing is we've got, so we film these people, and we have some external coder rating their global expressive behavior on a 1 to 5 scale, 1 being no expression at all, 5 being sort of complete, sort of huge levels of expression, okay? So this is our design. So what we want to do is start by jumping in, taking a look and seeing what we got going on here in terms of making sure we're meeting all of our assumptions, okay? So what we're going to do is we're going to start by, well, and what I've done, if we look at SPSS, right? We got our subject number, we got our film condition, instruction condition, and then what I've done here to just expedite things for our demonstration is I have a condition variable here. And I see 1 is sad express, sad inhibit, humor express, humor inhibit, right? But if I didn't have this in here, a nice way, so one way I might go through and calculate this quickly is I might sort by film and sort by instruction, and then just go through and say, all right, well, this is condition 1, and drag that down until we all right, there's all people in our first condition. And then you go down through, right? So you see, oh, these are all people in condition 2, right? Condition 3, condition 4. But we don't need to worry about that for right now because I've already done that. But you may need to do that as we move forward with stuff, okay? So what we're gonna do is we want to go through and start by looking at distributions within each cell. So what I'm going to do is I'm going to go to data, I'm going to go split file, and I want to look at condition, organize groups by condition, and I'm going to paste that into my syntax file. And then what I'm going to do is I want to go through, I'm going to analyze descriptives, and I'm going to look at expression rating, because that's my outcome, right? I'm going to go options, skew and kurtosis, continue there. I want to save standardized variables, because I want to calculate z-scores, and then I'm going to go through and hit paste, okay? So, what I want to do, and then go through, run all of this together. So what it's going to do, remember, for our group-based analyses, we always want to split these into individual cells, individual groups. And so how many populations am I looking at? How many populations have I sampled, or hypothetical populations have I sampled in this 2x2 design? 4, right? So I got 4 different hypothetical populations. So now instead of like on our t-tests or our one-way ANOVAs, I want to make sure that I'm looking at all this stuff individually, okay? So I'm going to go through and I'm going to run this. There we go. Okay. So I can go through and sort that, sort this, right? And then my express condition, sort this. Okay. Looks like I'm missing 3 values. okay? And so what I want to do is I want to make sure that I go through and mark these. So I'm going to go through File, Save As, call that Scrap. Okay. And so what I want to do for my screening, I want to make sure that I'm marking down what variables are missing, do I have missing values on, right? So which variable, or which participants am I missing expression scores on? I'm missing someone, or participant number 112, 32, and 200, right? And then I also want to make sure that I'm marking down what condition they were in, right? So I have someone in a SAD express, someone in a SAD withhold, and a humor withhold. Okay. So given that we're working with 192 people, am I too concerned about these 3 people with missing values? Haley, you're shaking your head no. Why aren't I probably too worried about this?
Because they have a large sample size.
Yeah, I have a large sample size. Now, if I was missing, say, 20 cases, and they were all from the same condition, would I be concerned about that? Yeah, probably, right? But here, looks like maybe something went wrong, so so we didn't get the video equipment right. So we've got 3 cases that are missing, 3 cases that are missing data. We want to go through, document those, document what condition that they were in, and then go through and get rid of those. Okay? Questions about this? All right, so I'm going to go down through and get rid of those guys. Delete that, and then I'm going to delete Z Express. I don't think that shouldn't make a difference, but just so we're working with a clean set. So we're now working with a set with 189 individuals. So I'm going to go through, and I've sorted it, so that's taking my split file off, right? So I'm going to rerun the whole thing again. All right. So these numbers aren't going to change because it wasn't going to run things for people I didn't have outcomes on anyway. But what am I going to go through, Kate, and maybe take a look at first across this output? Okay, I might look at me, but at this point I'm not super interested. It means what might I look at first? What do you think, Amanda?
I actually have a question about this. You want to look at your minimum and max to make sure that the answers are within the range?
Perfect, yes.
My question is, what if you have one that's not?
Okay.
What, do you find that person and exclude them, or what do you do with it?
Yeah, what do I do if I find someone who's out of bounds? Get rid of them, right?
Okay.
There's something weird with this, right?
So if one of them, if it's 0, or if it's 1 to 8, and you have a 0 as a minimum, you need to find that person in there and get rid of them?
Yeah,
Okay.
yeah. And then this came up while you were out, sort of during the break, with problem 2. Are you thinking about problem 2 in the set? Yeah. At one point, I had people doing a screening for that, and if you're doing a formal screening, you would have caught that person and thrown them out. But I think last year, I was giving people a break, told them they didn't have to do a screening on that. Then there's stuff that you need to throw out that you didn't catch. So I'm going to go back through and I'm going to say, okay, this is the set that you should be using for that, so you don't have to worry about, or I guess Angela and I don't have to worry about different people with slightly different results because some people threw someone out and some people didn't. Okay. But yeah, in general, you're exactly right. That's what we're doing with this screening, is we want to make sure that everybody falls into bounds. If people aren't falling into bounds, then that starts to become concerning, right? We've got an error in the data. If we say these scores can range from this to that, then if we've got someone who's falling outside of that, there's something weird going on, so we need to flag those people probably. If it's our data, we probably want to check the file, make sure it's not a data entry something or something along those lines. But if it's weird, want to go through and eliminate those people. So, okay. So we're looking at minimum, maximum, so we're all within range with these statistics. What else, Nick, might I be looking at before we get into skew kurtosis stuff in terms of evaluating? There are things I should be aware of moving forward with analyses.
Before you go to skew kurtosis?
Yeah. Okay. We're about there. What, John?
Are you gonna check the sample sizes?
Yeah, I want to go through and take a look at my cell sizes, right? Because my concern is like sort of, to what extent do I have to worry about wildly different cell sizes? Okay. Evelina, what is my, am I worried about differences in cell sizes in this design? Not too much, right? I mean, they're not exactly the same. It's not perfectly balanced, but I've got 44 people in my smallest cell, 51 people in my largest cell, so we've got a difference of 7 people across my largest and my smallest cell, but I've got pretty good cell sizes here, right? For an experimental study, feeling pretty good about this, right? So, but always wanted to go through, because this is going to start to give you information on about whether or not I have a balanced design. I have to start worrying about sort of compounding difficulties there, okay? So cell sizes aren't identical, but they're sort of similar. All my values are within range. Now I'm going to jump into skew and kurtosis values, okay? Haley, am I worried about skew and kurtosis?
Not really.
Not really, right? Looks like I have some positive skew, and depending on what I'm, so differences in kurtosis, we got positive kurtosis for people in the humor inhibit, negative kurtosis in people in the humor express, right? So some differences, but not anything that's looking too severe, right? And someone remind me, what's my assumption in terms of the distribution of my observed data? Do I have any assumptions about the distribution of my observed data? What's my distributional assumption for a means-based test? Not as non-central. What's that?
Just a normal distribution.
Okay, normal distribution. What if my data aren't normally distributed? You know, is it do I have a violation of my assumption?
No, it's just something we need to be aware of.
Okay. And it can be problematic depending on sort of how things are looking. Remember that for our grouped data, right? I'm technically not, sort of the assumption of my statistical test isn't about the observed data. Right? I mean, the actual data that I see isn't the main assumption here. What's my assumption with means-based analyses? Not that my data are normal, but what? Distribution of sample means is normal, right? And under what conditions does my distribution of sample means start to become normal? One, if my sample size starts to get big, and then two, what else? If it's pulled from a normal distribution, right? And this is an incredibly important thing to think about, right? So I can have skewed data, right? But that's not a violation of my normality assumption, because my normality assumption applies to the distribution of sample means, right? And so if I have skewed data, my distribution of sample means, and so let's say I have, for example, if we think about, like, I'm showing someone something funny and asking them not to laugh, to try and pretend like they're not experiencing anything at all. Is the distribution of those scores in the population going to be normal? No. What are they going to be? They're going to be positively skewed. Because most people are going to be pretty successful, but some people aren't. And so we're always going to have a positive skew, right? So what I'm measuring in the population isn't normal. But when does how does my distribution of sample means start to become normal? When my sample size starts to get large, right? And are we working with reasonably large cell sizes here? Yeah, we are, right? So now, like Amanda, you were talking about, right? If I got wild positive skew in one thing and wild negative skew in the other, then that might start to become problematic, right? Particularly if I have differences in homogeneity variance or something along those lines. But here, we've got, looks like some degree of positive skew across all of these, right? Again, one of the benefits, we're working on a 1 to 5 scale. Can we really have outliers on a 1 to 5 scale? Not really. I mean, if everybody was 0 and then I had 2 people at 5, that would be problematic, right? But if I get rid of those, then everybody's zero. I don't have a variable, I have a constant, right? And so here, thing we're wanting to keep in mind is that, again, even though these data might be a little bit skewed, our concern is with the distribution of sample means, not necessarily with our observed data. Now, as our sales sizes start to get small, or we start to have massive differences in cell sizes and sort of large discrepancies in variability, or things looking in different directions, then that starts to become problematic. But again, an assumption of our means-based test is not that our observed data is normal, it's that the distribution of sample means is normal. Okay? So things are looking all right here. What we're going to do next is I'm going to go through, turn my split file off. I'm just going to go through, sort that by participant number to click that off, because what I'm going to do now is I'm going to go to Analyze, Descriptives, Explore. Who's running Explore with their split file on? Nobody's done that? Yeah. What does it give you, John? It gives you an error, right?
Yeah, it's a mess.
Yeah. So here we're going to go through and we're going to drop our condition into our factor list, our expression rating into our outcome, and then our subject number down here in our labeling cases. Okay. On plots, I'm going to ask for histograms. I'm going to turn off stem and leaf. Okay. And then you guys can hit paste. I'm just going to hit OK. All right. It's given us all of our different information here. What I'm going to start doing is I'm going to look at my histograms for each one of my different groups. So again, we're seeing some positive skew-ish, right? We got a nice step function here for, and again, always remember to think about like what we're actually measuring. We're asking, so here we're looking at people who we've showed a SAD film, and then we've monitored their expression. We see people across the full range, but for the most part, right, with some people showing increasing levels of global expression. What's going on here? What do you think, Evelina? These are people who showed a SAD film, and we've told them to inhibit their expression. Again, this is got a 1 to 5 scale.
The frequency of expressed emotion. So people in this condition are more likely.
More likely? So 1 is no expression, and 5 is a ton of expression.
So less likely.
Yeah, right. So these people look pretty good, right? If we compare them to the people who we were allowed to just freely express our emotion, we see lower scores here, right? And so the highest scores, we got like one person at 3, right? So for the most part, people are doing a pretty good job of shutting down anything that they might express in this, right? If we look at our humor expressed, so these are people who are showing a funny film, right? Again, nothing too remarkable in terms of this distribution. We start to see some of that negative kurtosis, kind of a boxy kind of distribution here. But then if we go through and we look at humor inhibit, again, we're seeing that for the most part, people are doing a decent job of inhibiting their expression. But again, when presented with a funny film, stuff's leaking through, right? Maybe a little bit more than what we saw with the people who were watching the SAD film. Okay? We'll go down and take a look at our, but these histograms in and of themselves aren't too remarkable. We might talk about some positive skew, some boxy distributions there. We start taking a look at our box and whisker plot here. You see some different stuff, right? There's some things we might want to remark on in terms of this, right? So, Layla, what are you seeing in terms of is going on with your box and whisker plot here?
The inner quartile range for the different conditions, humor expresses a little bit closer to a 5 as opposed to The other conditions,
Okay.
they're closer to
Okay.
one for the expression ratings.
Mhm.
Um,
So again, if we're thinking about median values, right, the center line, we're seeing differences in median values here across the three conditions. Our interquartile range looks to be about the same for both of our express conditions, although sort of our humor express seems to have sort of more variability here than our sad express, perhaps. What's going on right here in terms of our quartiles? Emilio, if we're looking at our SAD inhibit, what happened at the other end of our interquartile range here?
It's a floor effect, the median is clustered at the bottom.
Yeah,
So almost
exactly.
everything's at the bottom.
Perfect. Well said. We've got a floor effect, right? The median value is the same as the first quartile all at once. So 1 is the median level, 1 is the median, 1 is also the first quartile, right? So everything's kind of stacked up on the floor. And again, what about this? What's happening here on humor inhibit?
On the median and the third quartile.
Yeah.
Same value.
Median and third quartile are the same value here, right? And then we've got these values here. These are values that are falling above 1.5 times interquartile range here, right? And so this starts to become a nice way. This is a better way of pictorially sort of looking at the distributions across your different conditions relative to histograms. I mean, histograms are nice at looking at normality and things like that, but this is where some of your box and whisker plots start to look nice, because you can start to line them up and stuff. Okay, so here you just want to describe in your screening kind of what's going on with the box and whiskers, and sort of talking about interquartile range and medians and values that are maybe extreme or falling outside interquartile range, things along those lines. But again, anything that's super concerning about distribution stuff here, not too much, right? So we're going to go through, make sure we're recording that, and then last thing we're going to do is we're going to go through and take a look at whether or not you have outliers based on your z-scores, okay? Now, what I'm going to do is I'm just going to copy my syntax here. And I'm going to go through, because I've got my split file, right, and my descriptives. I'm going to say, okay, I want to look at z-express. Don't need to save anything. And statistics, mean, standard deviation, I pull out skew kurtosis. We don't need to look at that again. Okay, so I'm just going to run this. So, Haley, what am I looking at here?
Your minimum, maximum.
Yeah, my minimum, maximum. And am I seeing anything that's hugely concerning in terms of extreme values or outliers?
The only one that might be concerning is the maximum for humor inhibit.
Yeah, right. So my humor inhibit, I've got some people who I've showed them a funny film and I've told them not to express, but it was too funny and they couldn't help themselves. Most people were able to, some people weren't, right? And so what I would want to do is go through and maybe go back up and take a look at, so here I would want to note that I do have some values, at least one value that's falling about 3 standard deviations above the mean, but I've also got a value for my SAT express that's close, right? So I might want to note that. If I go back to my data and sort this, and I can go down through and I can find, okay, it looks like case 242 in my humor inhibit condition, they have an expression rating at a 5, right? And that's about a little over 3 standard deviations above the mean. Also see here a person in my SAD express condition. I told these people to just emote naturally, but this person was apparently very emotive. That the SAD film got him, right? they were upset. And so this person is approaching 3 standard deviations above the mean, again with an expression score of 5. But if I go through and I take a look at my output, okay, here's my person in my SAT express condition. Here's my person in my humor express condition, right? So these values are all continuous members of the distribution. It's a 5-point scale. You can only really be so far. With cell sizes of about 50, are we concerned that these are going to throw off our mean terribly? Not too concerned about that. And thinking about, are these individuals that are a population of interest? Yeah, right? Because if we're looking at people's ability to regulate the expression of emotion, some people aren't going to be able to do so good. Like maybe a lot of people are doing pretty good. Some stuff's leaking through, right? But we don't want to start throwing people out just because they weren't able to, unless there's something about this condition that makes it essential that they absolutely cannot express high levels of emotion, right? We're probably going to keep these people in. We're going to say, yep, you know, not our manipulations don't work for everybody, so we're going to go through and maintain these folks in here, right? So we've gone through and we've taken a look here after we've gone through and described what's going on with sort of values that are of note. So we've gone through, we've taken a look, made sure that we identify cases with missing values, right? We've gone through and made sure that values are all within acceptable range. We've gone through and we looked at our univariate distributions. We've looked at skew, kurtosis. All those seem to be in range. Our histograms we might want to talk about. Looks like some positive skew on a couple of different conditions, but everything looks like it's a continuous part of the distribution, right? It's not like we've got everybody rating 1s and 2s and then sort of like 3 people with 5s, like a big gap, right? Everybody's sort of general distribution there. We've sort of looked at our box and whisker plots and kind of described what's going on. We've looked for extreme values or outliers, identified cases with notable z-scores, identified what those cases are, what values are causing them to be high values or low values. What's the last thing that we need to go through and think about in terms of assumptions for our ANOVA model here? John? Homogeneity of variance, right? And so what we're going to do when we actually go through and run our ANOVA model is we'll go through and look at a homogeneity of variance test and see kind of if we have any difficulties there. Which might we in this study? We might, right? I mean, if we go back through and we take a look at this, right? It's possible we could get some differences in terms of the variability we see across condition expression, variability in expression across some of these different conditions. So we'll go through and pick up with that in our last class. Okay. So, all right, folks, nice work. Thanks for hanging in there.